Hello. So this is joint work with Rahul Jain from Singapore. He's here. Also with Thomas Watson. He's starting as a professor at Memphis. Didn't really bother showing up. So this work is about proving lower bounds on the size of linear programs that express interesting polytopes. Typically, we care about polytopes that appear in combinatorial optimization. But really, for any polytope P, you can define its extension complexity as the least number of inequalities in a linear program that captures it. So here, if the polytope is n-dimensional, you have n variables in your LP, and maybe some auxiliary variables as well. So to be perfectly mathematically precise, what we're looking for is the least number of facets in maybe a higher dimensional polytope that projects onto the polytope you care about. So this picture is actually plagiarized from every talk on this subject, explains the principle. So I'm looking for expressing this two-dimensional 8 facets, as the projection of, in this case, a three-dimensional polytope with only 6 facets. So I save a little bit when I'm expressing things as projections. For some polytopes, you can have exponential savings. Of course, we believe that for polytopes that are associated with NP-hard optimization problems, this shouldn't happen. And so this study, it's a fun history to it, which you can read on this famous P versus NP page, listing attempts to resolve our central question. In the 80s, there were attempts to formulate the traveling salesperson problem as a polynomial-sized linear program. And in response to this, Mihail Yannakakis had this idea that you could actually show unconditionally that this couldn't be done. He managed to do it, prove exponential size lower bounds for linear programs, at least under some symmetricity restrictions. So he left open, as a main open problem, whether you could prove such lower bounds without these technical restrictions. And this was achieved in this recent work of Fiorini and others from Stock 2012. I think it's the best paper from that conference, and they were the first to prove exponential lower bounds using techniques from communication complexity. So in fact, they used techniques that were introduced after Yannakakis' paper, and the paper, in fact, initiated a small flurry of work in this area. Of course, we're not very independently minded people. We're just going to follow the crowd and also study this trendy area. So we have a contribution. Our main result, and really only result, is that we construct a family of graphs whose independent set polytopes are nearly maximally hard. So an independent polytope of a graph is just the convex hull of its independent sets, or really the characteristic vectors of independent sets. This result should be contrasted with what was known to hold simply existentially. So if you take a random 0, 1 polytope, so that's a convex hull of 0 on vectors, then most of these polytopes are really hard. Their extension complexity is 2 to the n. So this is a counting argument due to Rothwas. It existed even before we had these first explicit examples. Well, the explicit examples we do have, quantitatively, they're only exponential in root of the dimension, so root n. So we have such lower bounds for cut polytope, TSP polytopes, and Rothwas proved such lower bounds for the matching polytope. So our result is the first to go above this root n barrier in the exponent. I should also mention that for these polytopes listed here, the root n in the exponent, it's optimal. So if you wanted to find harder polytopes, you had to look somewhere else. And also, from these results, just by reductions, you would get exponential in root and lower bounds for the independent set polytope. So our result is merely a quantitative improvement over previous work. But still, an interesting aspect of the result is that the way we prove it. So I'm going to talk at length about our inspiration for the construction of these graphs. It has to do with a little-known connection that was observed by Frubesh between two seemingly unrelated areas of complexity theory. So extended formulations on one hand, and circuit depth complexity, or formula complexity as it's characterized by these KW games, Krachmann-Victorson games. I'll tell you what they are in a minute. So there's this little known paper of Rubesch where he mentions this connection. We are simply the first ones to actually put the connection to some use. It's a simple enough connection that I feel like I might be able to explain it to you, even if you haven't seen extended formulations of these Krachmann-Victorson games before. So just as a highlight overview of what this connection allows you to do, here's this one interesting example. I have here a screenshot from our favorite complexity blog by Lance. He's highlighting Rothfuss's result on the extension complexity of the perfect matching polytope as the complexity result of the year 2013. And he's writing that this lower bound, it's reminiscent of developments we had for monotone circuits in the late 80s. And here is a representative result in that line of work by Raas and Victorson. They showed that the matching function, which takes a graph as input and outputs yes if it contains a perfect matching, it's a monotone Boolean function. Its monotone formula complexity is exponential in a number of nodes. So of course these two results, they're superficially very similar looking. But now this connection I want to discuss, it makes this connection formal and not only superficial, but there's a simple black box fashion in which Rothfuss's result implies the Raas and Victorson result. So this connection wasn't recorded in the literature, even though it's just an instantiation of this general principle. And even at this very high level, you're kind of thinking, okay, formula size lower bounds, they've been studied a lot. It's a classical subject. So wealth of material there. What else could you find in that area that you could possibly strengthen into some result in the area of extended formulations? Okay, so that's exactly what we're doing in this work. So this work came to be by starting with this previous result I had with my PhD supervisor, Tony Kutassi. So we constructed an explicit n-bit monotone Boolean function with nearly the maximal possible monotone formula complexity. And now this abstract connection points to that there might be some particular construction in the extended complexity world which we go and find. So yielding these explicit polytopes of nearly maximal extension complexity. So at a high level. So let's try to actually go into details and understand this connection. I feel like I'm an ambassador for this connection. It's the one takeaway from this talk. I mean, our result is just kind of an application. So what are monotone Krachmann-Victorson games? This is a classical thing. So with any monotone Boolean function, you can associate this communication game where we give Alice a yes input to the Boolean function and Bob a no input. And they need to communicate deterministically and figure out a coordinate where the two strings, the yes and the no input, differ in this monotone fashion. So Alice has a 1, Bob has a 0 in that coordinate. It's a search problem. Its deterministic complexity characterizes, you can say, either the monotone circuit depth of the function or either the logarithm of the monotone formula size. Okay, on the other hand, we have this world of extended formulations. Janakag has already characterized the extension complexity of a polytope in terms of the non-negative rank of its slack matrix. So first, remember that non-negative rank of a non-negative matrix is just the number of non-negative rank 1 matrices you have to add up to represent your matrix. So it's like rank, but everything's non-negative. The slack matrix then associated with a polytope is defined here. So let's say we have this polytope P defined by a bunch of linear inequalities. Associated with it is the slack matrix whose rows are indexed by the facets, so these linear inequalities, and the columns are indexed by vertices. So for each facet, each vertex, the slack matrix contains the slack between them, the distance from the vertex from the facet. Really, it's the algebraic distance. It's a non-negative quantity. Okay. So this is Yannakakis' characterization. I also want to use an alternative phrasing for alternative perspective to thinking about non-negative rank. This is from this Feinzer's recent work. You can think of the log of the non-negative rank of a non-negative matrix as a kind of a weird type of communication complexity measure. Here we're looking for randomized protocols whose acceptance probabilities are the entries in the matrix. So of course, general non-negative matrices can have really large values, greater than 1. But if you scale all these values down uniformly to small enough numbers, you can view them as probabilities. So they have this characterization that the log of the non-negative rank of a matrix is the least cost of a randomized protocol whose acceptance probability is proportional to the entries of the matrix. So an input x, y, column, row, you're supposed to accept with probability proportional to the entry. Right, so I'm moving towards making this connection formal. And with any monotone Boolean function, I can associate canonically a polytope. It's the convex hull of the yes inputs. It's an interesting polytope. And here I highlight some interesting inequalities for the polytope, which express the fact that on any input x and y to the Cauchy-Victorson game, there exists a solution to the game. I express this fact as a linear inequality. So I have x and y, and I want to say that there's at least one coordinate solving this Cauchy-Victorson game. So linearly, I just say I sum over all indices where y has a 0. So at least one of the xi's, corresponding xi's, should have a 1. So the sum of them is at least 1. So it's a linear inequality that's valid for the polytope. So you can then, it's a kind of a facet, so you can look at its slack, which again was the left-hand side minus the right-hand side. It's a non-negative quantity. So this slack appears in the slack matrix. In this, I've identified a sub-matrix of the slack matrix. It doesn't capture the whole slack matrix, but a small part of it. It's an interesting sub-matrix. That's what we're going to consider. And just let me read out loud. What does this slack quantity compute? So it's the number of witnesses to the Cauchy-Victorson game. It's the first thing, minus 1. So I'm going to give a name to this submatrix, or the complexity of it. It's the number of witnesses minus 1 game. Very innovative naming. So here the input is again the same as to the Cauchy-Victorson game, but you're supposed to accept with probability proportional to the slack, which again is the number of witnesses minus 1. The complexity of this game is just lower bound in the log of the non-negative rank of this submatrix identified. So if you prove lower bounds on this game, you get lower bounds on the extension complexity of the polytope, which was the convex hull of yes inputs. Okay, so here comes the connection. It's really, really simple, breathtaking. The number of witnesses minus 1 game is easier than the Cauchy-Victorson search problem. So it's a really simple connection, and the proof is also really simple. It's a 2-line proof. So I claim that somehow if you can solve the search problem, you can solve this number of witnesses minus 1 game efficiently. So assume that we have an efficient protocol for the search problem. So what do? Well, you basically just at least run this search protocol once to find a particular witness. That's the first step. Complete this protocol somehow, make it into a randomized one that accepts with probability proportional to the number of witnesses minus 1. So the minus 1 is going to correspond to the witness you actually found, this particular one. So the second step is just you sample a uniformly random witness or input coordinate distinct from the one you found. And you check whether that's a valid witness to the Cauchy-Victorson game, accept if it is. That's a protocol whose acceptance probability is proportional to the number of witnesses minus 1. Now, you've seen something like this before. Yesterday, Robert talked about this Rasparov's magical rank lower bound method. what we're doing here, and this is how Rubesch came up with this connection, is that it's a non-negative analog of this Rasparos method. In Rasparos method, maybe you remember that there was this magical matrix. In our setting, it corresponds to the slack matrix. And it shouldn't be obvious exactly why these are analogous, but you have to stare at it for a while. Okay, so I really feel like this connection is something that if you work in either of these areas, you need to be aware of. It's underappreciated in the literature. Okay, so in the remaining time, let me say something that's particular to our work. This connection, simple as it is, it pointed us to the right direction. What should we be proving? We should be strengthening an existing result. So how do we actually go about proving that? Well, so several people have come up to me in this conference and they have asked the same question. So Mika, do you even lift? Okay, and the answer is yes. So it's in particular, it's our main proof strategy. I was really surprised. I went through the schedule for the conference and RVFest workshops, and there are a bunch of papers that are either doing this lifting from query complexity to communication complexity. Either they're proving new lifting theorems or they're applying them. Actually, there's even a paper from the archive yesterday that proves a new query to communication lifting theorem. So it seems to be all the rage. Okay, so our approach kind of fits into this framework in that we also start with a problem in query complexity, a search problem. It's called the Titan search problem, quite well studied. With any search problem, you can associate number of witnesses minus one game. I defined it for Kachner-Victorson games previously, but you can define it for any search problem, any model of computation, whether it's communication, query, Turing machines, whatever. In the query world, you're just looking for randomized decision trees whose acceptance probability is proportional to the number of witnesses minus one for the underlying search problem. So for this problem, we can show a huge query complexity lower bound, linear in n. It's not even terribly difficult. So once you have that, you'd like to lift it into communication. So take your cite and search problem, whatever it is, compose it with some two-party gadgets to get a communication search problem. Now, we'd like to argue that the complexity is preserved when you do this, the complexity of the number of witnesses minus one game. And in some sense, there is a communication lifting theorem that is exactly tailored for this type of computation where what we care about is the acceptance probability up to scaling. There is a lifting theorem for that. Unfortunately, that theorem assumes that your gadget size is something like log n bits per party. And that turns out to be completely, it's really bad for us. In our application, we absolutely need to have the gadget size be a constant. The existing lifting theorems, they don't have this gadget size down yet. So we can't quite apply, in a black box way, existing stuff. So instead, we just give like an ad hoc argument that for this particular problem, the complexity is preserved when you compose with some constant size gadget. That's kind of the main technical thing in the paper. And again, we shouldn't be doing that. Somebody should just go ahead and prove a general theorem saying that you can always do this with constant size gadgets. But okay, that's a major problem. So then you're in the communication world, you have a search problem whose associated number of witnesses minus one game is hard. It's known that you can take any search problem and reduce it to the monotone Kachner-Victorson game of some monotone function. It's a known reduction. The reduction is efficient if your search problem has low non-deterministic complexity. And this is something we very carefully control that holds for in our case. So then you already have now a monotone Kachner-Victorson game whose number of witnesses minus one game is hard. So take the convex hull of the yes input. That's an explicit hard polytope. And if you like, as a very last step, you can reduce this polytope to an independent set polytope. That's very much like an NP hardness type reduction, really standard, not particularly interesting. Okay, so that's just a very quick overview. So I mentioned here a bunch of open problems related to extension complexity. These are maybe some of the more famous ones. Can you prove lower bounds on the extension complexity of explicit matroid polytopes? Can you separate LP versus STP extension complexity for polytopes? And I'm just asking you food for thought. Can you use this wonderful connection to suggest an approach to these questions? Okay. So that's everything. Thanks. Right, so it's kind of hidden in here. So when we're doing this reduction at the very end, we want a search problem, reduce it to a Cauchy-Vickerson game. I said that the reduction is sufficient only if your non-deterministic complexity is small. And if you use gadgets that are that large, you blow up the non-deterministic complexity. You blow it up from log n to a large constant times log n. And you kind of lose exponentially in your non-deterministic complexity. So it's, you can't use that.
Any other questions? So what you're showing is sort of the reverse direction of this Frobisher's connection for a specific problem. Do you know that it can be generalized?
Do you mean does the connection work both ways?
Both ways, yeah.
Good question. I have a longer talk on this where I actually give a counterexample and discuss that you can't have the connection be both ways. So that's why we really say that these are strengthenings of the Cauchy-Vickerson result because there's no generic way to go the other way.
Let's thank Mika. Okay.